Alright, welcome back to our slides on graphs. We're going to finish them up this time. There are not many slides left, but the ones that are left are pretty dense, so it'll take a while to get through them. So, the last stuff that we finished talking about was special kinds of pieces of graphs, special kinds of cycles and paths that you can move around in, and a very, very hard problem called the traveling salesperson problem that works on weighted graphs, where there are weights up between all of the vertices along all of the edges, telling you how much it costs to move around. So let's talk about just moving around in general now. The word for that is called a traversal of a graph. Okay, so let's get into this. So a lot of the time, especially for like a traveling salesperson problem, but it doesn't have to be that fancy, there are a lot of cases where you want to take your graph and you want to go everywhere possible. You want to go everywhere inside of it. You want to visit every vertex, potentially. Or maybe there's one special vertex you want to search for. Okay, those are your two options that come up very, very often in graphs. So maybe, for example, you're stuck in a maze and you need to know how you're going to get out of that maze. So you have to try all the possibilities. Okay? That's the idea. So yeah, I'm going to teach you all the cool algorithms about traversals now, and then actually in the next chapter on trees, which we already know about, we will look into the theory. Okay, but let's get into the practice first. And so yeah, let me show you how this this maze is really a graph. So let's say that we want to go from the start, and like here's the start, to the end, here's the end. We can just pretend that these are nodes. Starting node, ending node, and I need to find a path that goes through the maze correctly, right, to get to the end. And so what you do is every option, you make a node in the graph. So these are all connected. Like I can go from here to here, here to here, here's another step. I can go in this way, but this is a dead end, right? So we keep on checking, trying all of our possibilities. We get there. Darn, we have to like backtrack, go back to somewhere else, try a new possibility, and that will lead us here. But do you see how this is a graph? And it will allow us to explore if we try all the possibilities. Like you can go this way, go this way, go this way, and eventually you're going to find your way out, right? Maybe you look this way a little bit, try going this way, but it leads you to a dead end. But as long as you keep everybody connected, like you follow only edges that exist, like, oh man, again I hit a dead end. But eventually, if you try all the possibilities, you visit every place, every vertex, following every edge, if you do this kind of traversal, you will eventually get to the end of this maze. And so that's how you can represent a maze as a graph. Isn't that cool? So that's a thing. Another thing is maybe there are multiple ways to move around in this graph and get from start to end. We might care about doing it in the minimum way. So you can also think of traversing when like you have weighted edges involved. Like I'd rather go across a weight 50 edge than, like if I'm starting here, I'd rather go across a weight 50 edge than a weight 100 edge, for example. Okay, so that's the idea. Traversal just means I want to go places. I want to visit every vertex, or maybe I want to visit just enough until I find the thing that I'm looking for. Okay? So that is our goal, and there's a bunch of different ways to do it, and let's talk about several of them right now. Okay, so the first is called depth-first search, and this one involves, usually it's implemented using recursion, but I'm going to teach it to you using a stack. So secretly the recursion is happening in the stack, okay? The idea of depth-first search is that you want to go as deep as you can into the graph. Try and like say you're starting at A, go as far as you can, follow as many edges as you can until you give up and try a new path through the graph, okay? This will make sense when I give you an example, all right? So go as far as possible without having to retrace your steps. That's what depth-first search tries to do. And we'll talk about its time complexity, but the idea is it's going to either, depending on the graph, it's going to eventually go through every vertex, right? So it's going to visit every vertex constant time at each vertex. So it's either that much time, or if there's more edges, we're going to also try and visit all the edges. So it's just whichever of those two win out. It's like the maximum of the two. And so it's kind of like we have two variables. we're visiting all the vertices and all of the edges, doing constant work along each edge and at each vertex. So the sum is our running time. I hope that makes sense. We have two variables now for once. And so we have to sum them together because we're not sure which is bigger, which one wins out. All right, so yeah, let me show you depth first search, abbreviated to DFS. And it's always taking a graph in some form. Maybe we've encoded the graph as a matrix or as a list, right? An adjacency list. Remember our encodings. It doesn't matter. You have these options, right? Either way works. And then we want to start from a certain vertex. Okay, starting from a certain vertex in that graph, let us visit everywhere. Okay, and so we kind of come up with deep paths until we've seen everybody. Okay, so here's how it works. Let's see here. What do I want to have as an example? Let's say that we start at vertex A. Okay, and this is our graph G right here. Okay, and so we start at vertex A. That's the first one we're looking at. So the idea of a traversal is to visit everybody, and so we're going to keep track of a set of things that we have visited so far. Okay, that's the idea. And then also, we're going to keep track of where we've been along a path, which is going to make a stack. Okay, that's going to involve a stack. And so we make an empty stack data structure to start out, and we push our starting vertex into that stack. Okay, so at the very start of this algorithm, saying that we're starting at A in this graph G, our visited set is currently empty. I'm not going to draw a closing parenthesis because I'm going to add to it. And our stack right now has just the starting vertex in it. And so I'm going to draw a stack like a list, like a Python kind of list. And so it's just got A in it right now. And again, I won't draw a closing list symbol so that I can add to it in a second. Okay, so yeah, I'm going to write a stack like this. So if I write like this, A, B, C, think of it as encoding the stack like this. A on the bottom, then B got pushed, then C got pushed. Okay, so that's how I'm going to draw it down here. So let's go through this algorithm and see how it's going to visit everybody and work its way around the graph. And I'm going to try and remember to number the order in which the nodes get visited. That's important. And that will allow us to compare with another algorithm later. Okay, so while S is not empty, so while our stack is not empty, and it's not right now, it has A in it, but only A, then what we do is we pop from our stack. And popping, in this case, both removes something from the stack and it also takes it out. So we set V to be whatever the thing we got off the stack. Okay, so V is now A. Does that make sense? So we just popped A. And let me delete it. So now V is set to A, and now we need to see what we want to do with A, because we just popped A off the stack. All right. Well, if A is not in the visited set, and it's not right now because the visited set is empty, then we're going to visit that node A. Okay, because V is A right now. We're going to process the node, and this can be whatever you want it to be. Okay, maybe we're processing the node to just print them all out. Maybe we're processing the node to say information about it, like I got here from somewhere else. You can keep track of information like that, but visit, let's just make it be some black box. You can really do anything with the node at this point. Depends what it was. Maybe it was like a city name or something. Okay, so we process the node, and then we're done processing it, so we add it to our visited set. Whatever it was visited is now one more. And so we just visited the A node, okay, the A vertex in this graph. And it was the very first thing that we visited, okay, number one. And then, because we want to visit the entire graph, right, what we do is we push all of these adjacent vertices to S. So who's adjacent to A? We got B, C, and E, right? So we're going to push them all to the stack. And I don't know, let's just go in this order. B, C, and E. Doesn't really matter. And so here's the top of the stack now. Okay? That is the idea. So now we keep on going while the stack is not empty. And you see how we're adding more things, and we're eventually going to visit those things and then also their children. Okay? That's the idea of depth first search. So let's go and wrap back around. S is not empty. The stack has E at the top of it. So let's pop from the top, right? And let's take our E out, okay? So we're going to take our E out. And now we're working with E. Have we visited it? No, we have not. So let's visit E, maybe print it out, do something cool with it, and then add it to our visited set. We just visited E. It was actually the second thing that we visited. Yay. And then we will push all of its adjacent vertices to S. And who's adjacent to E? We have A and F, it seems. Okay? So you can see kind of how we're wasting a bit of work right now, because we've already visited A, right? There's an optimization that we could do here, but let's just follow this out word for word, line for line. So we're going to push A and F to our stack, and go from there. All right, so we keep on wrapping around. You see how this is going to find everybody that was connected to this original node A. Okay, hope you see how it's working. And so it's going to try and go as deep as it can through this graph until it can't go any further. Like, we're not going to try and find a cycle or anything. So, okay, S is not empty, pop it, so that's the F. Take the F off. Now we're working with F. F is V. Have we visited it yet? No. So process F, do something cool with it, add it to our visited set. Bam. And then push all of its adjacent vertices. By the way, it was the third thing that we visited. Push all of its adjacent vertices to S. Okay? So who's adjacent to F? It looks like it's B and E. So push them all. B and E. Okay? So this is what our stack looks like right now. And so we keep on going. So while it's not empty, it sure isn't. It's got 5 things on it. Let's pop the stack. So we're popping E off. And what do you know? We have already visited E. It is in the visited set. So we're going to do nothing. We're just going to wrap back around. And so that's how it's going to go away. Okay? And then we go back. So S is still not empty. Now B's at the top. So let's pop our B. Okay? Hope you see how this is working. We're going slow for a reason. So we just popped B, and let's see what we have to do with it. We have to, well, we haven't visited it yet, so let's visit it, add it to our visited set. B, that was the 4th thing that we saw. And then what we do is we push all of its adjacent vertices, A and F, to our stack. Oh, sorry, A, F, and D as well. Excuse me. A, D, and F. And so now I have some duplication in the stack too. Oh man, that's no fun. But I think I can go a bit faster now. I hope you can see the game that we're playing here. And so, okay, let's go back around. S is not empty. Pop the F, but we have visited it, so we're not going to use this if statement. Go away. And then we wrap back around to the start of the loop. Okay, pop the D this time. And we haven't visited the D, so let's visit it, add it to our visited set, push all of its adjacent vertices. So that would be, it's the 5th thing that we just visited. And then we're going to push its vertex B, right? That's the only thing adjacent to it. And then we're going to wrap back around. So do you see how we just made a very, very long way through the graph? We followed in this way. Do you see how we made a very deep traversal through the graph? And now we're kind of stuck and we have to follow a different route. Do you see how that happened? That's important. Okay? That is depth first search. That's how it acts. Okay? In a nutshell. So now we can follow the rest. So we're going to pop the B. We've already visited B. It's in the visited set, so let's not care about it. We're going to wrap back around, start of the loop. We've already visited A, pop it off. Again, already visited A, pop it off, and do nothing. And then we see C. Oh, that's now at the top of our stack. And so we're going to pop it. And what do you know? I have not seen C yet, so I'm going to visit it. Add it to our visited set. It is the 6th thing that I have seen. And then I am going to push all of its adjacent vertices to S. So I have A and G. A and G to our stack. Okay? That's the idea. So, okay, what needs to happen now? Well, let's pop the G off the stack. Hey, I haven't seen that yet. Cool, I can do stuff. I can visit it. Add it to the visited set. G, it was the 7th thing that I saw, and I will push all of its adjacent vertices, and there's only C left. Boop. And that is it. So now, I'm going to wrap back around. I'm going to use the stack, right? I'm going to pop the stack, like, okay, C's gone, but I've already visited it. Same with A, I've already visited it. Same with B, I've already visited it. Now the stack is empty, and I am done with my depth first search. Do you see how that allowed me to visit every node in the graph in a very special way? I went very deep first. I went from here to here to here to here to here. Then I had to like back up, and then I went from here to here. Does that idea make sense to us? That's what happened. Let me draw that in a different color, actually. That's the path that it took, essentially, through this graph. And eventually you're going to be like, oh, that's classic depth first search. All right, so that's what happened. And then we're done with our visited set. We have seen everybody. I can finally like close this off. That is what depth first search does. That's how it visits things. It goes as deep as it can, as far as it can, without having to retrace its steps. Okay, so that is depth first search. Do you see how long we took on this slide? That is going to be a pattern for the rest of these. Okay, so that's the first algorithm. Let's now talk about breadth first search. Okay, or maybe first, notice that this is a bit of a waste. We don't need to push, like, if we're down here talking about G, we don't need to push C again because we already know that it's visited. We're never going to visit it again. So we can maybe clean this up. We can clean this line up a little bit, and let's fix that in this next one, okay? So this one's called breadth first search, and it does kind of the opposite to depth first search. Instead of using a stack, we're going to use a queue, and that's going to make all the difference. Like the rest of the code's the same. We just use a queue instead of a stack. And what it's going to do is instead of searching wide through the graph, it's going to search, instead of searching deep through the graph, it's going to search wide through the graph. So it's going to, like, if we start at A, it's going to visit B, C, then E, and then start worrying about going any farther. Okay? That's its goal, and that's going to come out of the way a queue works. Okay, so stack versus queue, finally, we're doing something cool with them. Okay, so yeah, this tries to stay as close to the starting vertex as it can for as long as possible. And again, it's the number of vertices plus the number of edges time, because we're trying to visit all of them. Every vertex follow every edge. Okay? And whichever one of these is bigger is the one that wins out, right? So let me show you breadth first search now. So what it's essentially trying to do is like start here and go out a little bit, explore, and then go here, explore some more, explore as far as it can. It's going to make a nice looking tree like this, essentially, as it visits each level. Okay, there's like a concept of levels. See if you can catch that. Okay, so again, let's pretend that we're starting at A, visiting every node of the graph, using breadth first search. So the visited set starts empty, and our queue is going to also start empty, and it's going to have the starting vertex in it only. Okay, so this is our queue. It has A in it. Okay, so that is what our queue holds right now, and while it's not empty, we're going to pop it, take the front, right? We take the front thing from the queue, that's the A, and if it's not visited, it isn't right now, this is the first thing, we're going to visit it, add it to our visited set, cool. So it's the first thing we saw. And then our nice hack here is that we're going to not push every adjacent vertex to A. We're going to push all of the unvisited adjacent vertices to this thing, okay? To our queue. So we're going to push B, C, and E to our queue in order, right? B, C, and E. And so this is, I'm just going to draw my queue like this. A is not in it anymore. I crossed it off. Okay, so the front of the queue now is B. Okay? And so we wrap back around, and this is how it's going to, if it goes in order from front, you can see how it's going to visit B, C, and E next. It's forced to, okay? So the next thing we pop is the B, and we visit it because it's not in the visited set. Visit it, add it to our visited set. It's the second thing we saw, and then push all of its unvisited adjacent vertices, so forget A, but push D and F. Oh, oops. We'll push D and F to our queue. Isn't that neat? So that's how that's going to work. And sorry, we just visited it as well. So that's how that is going to do its thing. And then we're done visiting B. And now we wrap back around. Q is still not empty. It has C at the front now, so let's visit C. All right, we pop it. So we have not seen C yet, so visit it, do what you need to do, add it to your visited set. It's the third thing we saw. And then add any of its unvisited adjacent vertices to the queue. All right, so that seems to be our G node. So that's being added to the end, because you push to the end, pop from the front in a queue, right? So that's happening. And then we're off to the races again. We go back to the start of the loop, pop our E. It hasn't been seen yet, so we're going to visit it, do what needs to happen there. It's the fourth thing that we've seen so far. Okay, so that's that. Push all of its unvisited adjacent vertices to the queue. We've seen A, but we have not yet seen F. So let's push that. And so there is, again, a bit of duplication here, but that's not going to be a big deal. It's less duplication than before, right? So this is still a better line. So that happens, and then we're going to visit D next, because that is going to be what we pop, and we haven't seen it, so let's push all of its stuff. Okay? So that's the next thing that we visited. It's the fifth thing, and we push all of its unvisited adjacent vertices. It's only B, but we've seen it, so we don't push anything at all. Okay? And then I think I can go a bit faster now. We're going to pop the F. F is now V. We haven't seen it. It's not in the visited set, so visit it, print it out, do whatever you want. Add it to the visited set. It's the sixth thing that we have seen so far. And push all of its unvisited adjacent vertices. So we've seen B, we've seen E, we're pushing nobody. All right, then we pop our G, haven't seen it, cool, visit it, add it to our visited set, and it's the seventh thing that we've seen so far. We push anybody that's next to it that we haven't seen yet, but we have seen C, so we push nobody. And then finally, we are going to pop our F, but oh darn, we've already seen F, so we're going to skip over this, and now the queue is empty, and we're done with our loop. Okay, do you see how this is like completely different to how depth first search worked, and how it visited all the nodes in the graph? So this is how breadth first search worked. It like found this path, then this path, like go as wide as you can from A, kind of doing all this, and then like notice the next level of things. So from B, find here, and then from C, find here. We skipped over this one. Okay, so notice this, like this is the tree that it's filling out as it notices things, versus this stuff in green over here, the way that we filled out our path, our very long path. Go as deep as possible versus go as wide as possible. That's depth first search versus breadth first search. Okay? And those are two very, very common algorithms for graphs that you will see for the rest of your computer science career. Okay? So get used to these, get some practice with them, and let's keep on trucking. So let's next talk about Dijkstra. This is an algorithm that's named after somebody, named after Edgar Dijkstra. He came up with a shortest paths algorithm because sometimes, instead of just going in a weird way, going as deep as possible in a graph to find all the nodes, going as wide as possible in a graph to go and visit all the nodes, you have a third option, right? You can go, like say you're starting at A, you can find paths to each node that is the minimum path to get there. Like if I want to get to F, I'm definitely not going to go this way, right? Because that's 7 plus 9 plus 3 weight. I'd much rather go this way. Yeah? That only costs me 11 units of whatever, time, money, things like that, distance. So we would like to find the shortest paths from any starting vertex to every other vertex. Okay? That's what Dijkstra's algorithm does for us. Okay? So you notice that this is like a cookie cutter algorithm here. So I replaced, started here, had a stack, replaced it with a queue, and we got a cool different kind of search. If you replace the queue or the stack with a priority queue, you can actually find the shortest paths in a graph that has weights. Isn't that neat? So that's what we'd like to do next. Okay, so let's have a graph with like weights involved, and we're going to find the shortest path from a starting vertex to every other vertex in the graph. All right? And this has a very weird looking time that I will not prove to you right here. You can do it this way. This is the time that you get with a priority queue, because remember that that has a heap underlying it, which has like logarithmic time for accesses. And still v plus e is hidden away. And so it's kind of do everything that you did in breadth first search, but now you're popping things out of a queue. That's kind of my analysis there, but we won't have to get into that too badly. So that is the time, and it was invented by Dijkstra, which is, he's a very, very famous man in computer science. His name is going to come up a lot. He was around at like the very beginnings of computer science as it was getting started. He discovered a lot of very cool things in addition to this, and he just so happened to be the PhD advisor of my PhD advisor of my PhD advisor of my PhD advisor of my PhD advisor, I think. Okay, so like he's like my great 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 PhD advisor, grand PhD advisor. So that's fun for me, and so I'm kind of related to him in a sense. And if anything that I show you on this slide, it's a very complicated algorithm, but it's very similar. If any of that doesn't make sense, here's a very, very good tutorial. If you go here, there's a lot of cool animations or pictures as well, and it has like a Python-like syntax. So try this one out if you have any interest in it. It's very, very important in a lot of different areas, this algorithm, okay? It's a very common one to learn, and I'm excited to teach it to you. So it's called the Dijkstra shortest paths algorithm. It takes a starting vertex, just like every other traversal that we've seen, and it finds the shortest path to every other vertex in the graph. Okay, and so here's what it does. Here's how it looks. So essentially, we're replacing our queue/stack with a priority queue, and it's a min priority queue. Okay, and I'll show you what we're getting the minimum out of in a second. What we're going to do is we're also going to keep track of two things: a map from nodes, vertices in the graph, to distances, how far we think it takes to get there. And then also we're going to keep track of a map between nodes, from nodes to nodes, that shows where we came from, like who's the predecessor. That's what pred stands for. Who's the predecessor of me along the shortest path from the starting vertex to me, because we're always starting at some starting vertex. Okay, so priority queue or heap, that's what we're using here, and we're doing cool stuff with it. Okay, so yeah, we now have to keep track of a few extra things. This distance map, we can ask for like, what's the distance to the node A? It takes a node to the distance to that node in the shortest path. And then the predecessor map is going to tell us what is the path, what is the shortest path to this place. Maybe like you went from A to C to E and that's how you got there. So like in this map, we would store that the predecessor along the shortest path of E, we'd store that, we'd store C into it, because where did we come from to get to E along the shortest path? We came from C. That was the predecessor. Okay, so that's what we're storing there. Hopefully that makes enough sense. It'll make even more sense, I promise, when we do the algorithm on paper on the next slide. But yeah, now instead of all this, we have a priority queue, and we're pushing our starting vertex as normal, but we're also like, think of it as in a struct or something. We're keeping track of some extra information. Like we're pushing a bunch of things. We're pushing, in addition to the vertex, an idea of where we came from, an idea of the previous node, and then an idea of the distance that it took us to get here. Okay? So at the very start, like, there isn't a good value of where you came from. You should just be able to say null or something. But let's just say that the previous node in the path from the starting vertex to itself is the starting vertex. That's just a silly default value. You can change this to null maybe. And this is the distance from that node to itself. You can't do any better than 0, right? That's where we're starting, so the distance is 0 to get to the starting vertex. Okay? So this is the kind of information that we're storing into the nodes of our priority queue, of our heap, and it's a min priority queue, and we're popping based on this distance that we're adding. Okay? Popping based on distance. So we're always taking out the next thing with the minimum distance that we've stored up. Okay? That's the key. And so because we're pushing three things at once, a node, where we came from, the distance to that node that we think it takes to get there, all those three things at once, that is what we pop. We're popping three things at once. Okay, it's all one big struct essentially. And so that's what happens when you pop, and we're getting the node with the minimum distance. Okay, it's this part. That's going to be the smallest one left in the priority queue. And then essentially the rest of this is very similar. We visit the thing, add it to our visited set, and then here's how we process the node. Like we add its distance, add its predecessor, and then we're going to do some fancy stuff to calculate the next nodes to push. Where did we come from? The current node that we popped. What's the new distance? Well, it was the distance from how we got here plus the weight of that edge. Okay, so that was probably just a bunch of words that went over your head. Do not worry, I have an example. Okay, so, but I want to tell you all the little pieces first. So let's do this. See how we're doing on time. Yeah, so for the rest of the time today, let's implement on paper how this is going to run. Okay, so here's our graph, and let's pretend that we're starting at, let's do somewhere different this time. Let's say that we're starting at D. So here's our starting vertex, D, and then from D, we're going to go places. We want to find the minimum path from D to every other node in this graph, okay? That is our goal. Are you ready? So here we go. Our visited set starts out empty. Sure. Got nothing in it. We haven't seen anybody. Our distance map has nothing in it. It's empty. Our predecessor map has nothing in it. It's empty. Our priority queue starts out being empty. I'll just draw it like a list, I guess. And we'll pop it accordingly to the smallest distance. And then we're going to push to our priority queue these three things. The starting vertex, and we're going to store what the previous thing, the place where we came from. So our starting vertex was D. We're going to have a previous element. Where did we come from to get to D? Well, this is just a silly starting value. We could say null here if we wanted to, or we can just say D. It's like kind of wraps back around on itself. That's how we know it was the start. And then the distance to get to D was 0, because that's where we're starting. Okay, it costs nothing to stay at the starting point. Okay, so that's the priority queue. Right now, it holds just one thing, this triple of node, node, and integer. Okay, so that's our priority queue, and then let's begin. So, while it's not empty, it's not, let's pop our priority queue, get the thing out with the minimum distance. Well, there's only one thing in it. It is this thing, so D. All right, so we're popping this, and then we're doing stuff with it. We have not yet visited D, so we add it to our visited set. Cool. And then this is the next thing. This is the next best place to go from where we know to go. And so we're going to save inside of the distance map and the predecessor map. The distance that we stored here, that we just popped off, so that's 0. The distance to D we save as 0. And then the predecessor of D is, well, D itself. That's our silly default value. We could say null here if we wanted, though. Say the predecessor of D is D. D maps to D in this map. Okay, and then for every adjacent vertex that we have not yet visited, so in our case B, because we're starting from D, so every adjacent vertex that we haven't visited yet, so just B right now, we're going to push it. Okay, we are going to push that node, so B. We're going to set its previous element. Where did we come from to get here? Well, we came from D, so the previous element was D. And then what's the distance to get there from D? It's, well, how far was it to D itself? That was the 0. Plus the weight across this edge. It's a weight 5 edge. Okay, see how this is all coming together? And so it looks like the weight to get to B is 5, given what I know. At least coming from D, it's weight 5. Okay, so that's what we add to our graph, to our priority queue, and that's how we're moving around our graph. So we have just one more thing in this priority queue at this point. Let's keep on going. Okay, so now we wrap back around. Priority queue is still not empty. This is gone, right? I popped this, so there's only one thing left to pop. Pop the node with the minimum distance. We have no options right now, so we're popping this guy. B with previous as D and the distance as 5. Okay, so we have not yet visited B, and so this, in fact, perhaps is the best way to get there. So let's say that we have now visited B, and this is the best way to get there from D right now. The reason is because we popped it next. That was the minimum thing. We can't do any better. So we're going to take our B out and save how we got there. So the distance to B was the distance that we stored up in here. So it was 5. The distance to B was 5. And how did we get there? Who did we come from? We came from D. Okay, so save that the predecessor of V is this element right here, this node right here, D. So the previous element on our way to B from the start was D. Okay, you see how I'm adding those things? And then we're pushing all of the adjacent elements that we have not yet seen. Okay, all the things that have not yet been visited. So skip D, like here are all the possibilities of places that we can go from B. Skip this one, right? So we're going to push A and F. Okay, so let's push A. So A, previous being where we just came from. So previous is V itself, which is B right now. It's the node we're working on. And then the distance that we think we need to get to from A is the distance to B, which was 5, plus the weight across this edge, which was a weight 8 edge. So that is 13. Okay? So getting to A coming from B would take 13. Okay? And so then we'll do the same for F. We'll push that too. So we could go to F that was coming from B, and the weight to get there, the distance to get there, was the distance to B itself, which was 5, plus the weight across this edge, which is 3. So that's 8. Costs 8 to get to F from B right now. Okay? That's what we're thinking. Okay? And so that is how we're going to continue. All right, so now these two elements are all that are in our priority queue. I popped this one and this one. I'm just keeping them there for posterity. Okay, so that's what happened. Let's keep on going. Let's, while priority queue is not empty, pop the thing with the minimum distance. And this is going to cause some interesting things to happen. All right, so we're not popping this guy. We're not popping A. We're not visiting A yet. There might be a better way to get to A, because look at these distances. We're taking the smallest one. So we're going to pop this one. We are going to visit F next. All right, that is the best way to get to F right now. Okay, so let's save that along. We have just visited F coming from B. Okay, that is supposed to be a B right there. So coming from B with weight 8. All right, so the distance to F was 8. That's the minimum distance. And where did we come from to get to F? We came from B. So save all that along. That's these lines here. And then for every adjacent vertex that we have not yet visited, so F has B, which we have visited, and E, which we have not, so we're going to push E, do this. Okay? So we're going to push E coming from F, where we are right now, and the distance to get there is the distance to F, which is 8, plus the distance along this edge, which is 9. So that's what, 17? So that's one way we could get, potentially, to E. Maybe we'll find a better way eventually, but right now the only way we know how to get to E is across a weight 17 edge. That's kind of us coming along this way. Maybe this is a better way. I don't think it is though, right? So yeah, maybe we'll pop that one soon, but we always worry about the minimum one, and that's what gives us the minimum weight path for everybody. All right, so that's what I pushed. I pushed E. B we've already seen, so we're good there. All right, so that is now our priority queue holds this one and this one. Which one do we pop now? The one with the minimum distance. So we're going to A now. All right, so we have not yet visited A. So let's add it to our visited set. Let's save the distance to it. The distance to A is 13, and the way that we got there was through B. Okay, so we came through B to get to A. The predecessor of A in the shortest path is B. Okay, and we just popped it, by the way. Okay, and then from A we add we go across every edge to every node that we have not yet seen. Okay, so who have we seen so far? We've seen D, B, we've seen F, we've seen A. All of those nodes that we've seen so far, we're not going to worry about them. So skip this edge, but to C and to E, we're going to add those paths. Okay, so we're going to worry about adding C and E now to our priority queue. So here's what we can do. We can go to C from A, that's where we are right now, and what was the weight to get to C? It's whatever the distance was to A from our starting point, which was 13, plus the 6 it takes to get from A to C. Okay, that's how you compute this, and that is 13 plus 6 is 19, right? So that's 19 to get to C. That's the best way we know how so far. Okay, so that's that, and then we're also going to push E. We can get to E. So yeah, we have another way to get to E. Maybe this one's better. We can get to E from A along a 13 plus 7 path, and that's 20. So that's not a better path than the one that we knew before. All right, so those are the things that I add to my priority queue, and I keep on going. Okay, so now I have these 3 options of where to go next, and it looks like I'm going to visit E next. Okay, because that's the minimum distance among all the distances in the priority queue. All right, so that means I'm going to pop it. I'm going to pop this one, go into E. I'm visiting E. I'm saving its distance. Distance to E along the shortest path is 17. Where did I come from? I came from F. The shortest path goes through F. That's the predecessor along the shortest path. Okay? And then, so I visited E. I add all of its next nodes that I haven't seen yet. And, oh man, but I've seen A and I've seen F already, so I push nothing. Okay? And then we just go back to the start of the while loop. Still not empty. I have these 2 options. Where am I going? It looks like I'm going here. So CA19. So I'm popping this one, popping the C. I'm visiting C next. That's the next one along this shortest path. It looks like we're coming through A. So I'm visiting C through A, and the distance was 19. Okay? So the shortest path to C is 19. Costs 19 wheat, and I came through A to get there. Okay? That's how that one works. And then again, visit it, push anything that I haven't seen yet, so this path along to G. Push that to the priority queue. So we're going to push G coming from C with weight, where are we? It looks like it's weight 20, because it's 19 plus this 1 right here. Okay? So that's that. And yeah, now I have these 2 things in my priority queue, and which one do I pop? Just the one with the minimum distance? Well, they both have distance 20, so we can just pop arbitrarily either one. It's not a big deal. So let's just pop this one first. So that is E, but we've already visited E. And our distance was 17, much better than 20, so we're going to skip that. Okay? So skip that, and then we have just one left to pop. We pop our G. Okay? We have not yet visited G, so we're going to add that. There is our G. It's now in our visited set. And where did we come from? And what was the distance? So the distance to G is apparently on the shortest path. Short is apparently 20 from the start. And then where did we come from to get to G? It was C. That was our predecessor. Okay? And then we're going to add, I just visited this, all of the unvisited next adjacent vertices. Okay? But there's only one, it's C, and we've already visited C. So there's no use of coming back to it and finding a better path. There's no way for that to happen. Okay? So that will end this loop, because now the priority queue is empty. And so here's my visited set. I visited them all. Here's my distance map. Here's my predecessor map. And these two tell me the shortest paths. Here are the distances along the shortest path from our starting vertex D to everybody. And then here is the paths themselves encoded as where did we come from. Okay, so let me show this to you. Let's talk about maybe the shortest path from D to F. Like, how did we get to F, for example? Let's read this. Let's read what we built up. So the shortest path to F, this is how you would read it, is, okay, apparently it takes only 8. The distance from the start to F. The F node is 8. That's the shortest path. And what is the path? Well, we just follow this predecessor map in reverse. So we start at F. Okay, we're going from there to B. So we're coming from B. It's kind of like we draw it backwards. And then we go and look up B in the predecessor map. Where did we come from on the shortest path to get to B from the start? So it looks like B's predecessor is D. So we do this. And then D's predecessor is itself. That's how we know that was the starting vertex. And so now we're done. And this was the shortest path. So go from D to B to F. The weight was 8. And that's the shortest path to get to F from the start. There are other options, right? We could have come all the way around here, but that's much longer. That's not the shortest path. We have built up the shortest path from the start to any other vertex. And to look up that path, all you have to do is follow this predecessor map. Okay? So that was a lot. It was a very involved algorithm, but I hope that you can see how we got there, right? It's this idea all over again. We just change the data structure that we use, and we get some really cool stuff out of the deal, okay? We did need some extra information along to store in Dijkstra's algorithm where we come from and how to get there. That was important to save that extra information. But once we knew what to save and how to use it, it really was just a change of a data structure. That gave us the ability to find the shortest path from a starting vertex to every other vertex in the graph. That's super cool, right? So that is Dijkstra's algorithm in a nutshell. It's a very famous one. Feel free to look it up and consider reading this very nice tutorial page for some extra information about it. But that is graphs. That is all the slides on graphs that I wanted to talk about. Our next slides will be on trees. So I'll see you in that lecture.